Good morning, my name is Jenibelle Wievin with name 260-105632, along with my teammates Aidan Eka Prasojo with name 252-011934 and Lauren Abigail 260-108426. We are here to present our deep learning AOL report with the title of Comparative Analysis of Deep Learning Models for Multi-Class Disaster Image Classification. In this project, we will explore how deep learning can help improve emergency response by automatically classifying images of natural disasters. Natural disasters are a serious threat to lives and infrastructure. Fast and accurate identification using visual data is essential for quick response and resource planning. We developed a deep learning model to classify disaster images into 4 categories. There are earthquake, public fire, landslide, and water disaster. This dataset is taken from Kaggle, presented a challenge early on, class imbalance with water disaster having far more images than the others. This effective model performance is discussed further in the report. Disasters are increasing in frequency and intensity, largely due to climate change and urban growth, and the World Meteorological Organization reports a five-fold increase in weather-related disasters over the past 50 years, causing over 2 million deaths and trillions in economical loss. With growing access to satellite, drones, and social media imagery, fast classification is more important than ever. Study shows deep learning is effective in this area, enabling faster and smarter decision making. This project highlights how AI can support disaster management by improving detection, response time, and coordination. Up next, methodology. The approach for this work followed a structured flow of image classification based on deep learning. The main goal is to classify natural disasters from image data using convolutional neural networks, or known as CNN. This flowchart outlines the methodology. First, we have dataset selection and then data preprocessing. Up next, model building using CNN and efficient net B0. Then training and validation, and lastly, evaluation and results. First thing, we have to prepare the data. This dataset, again, is taken from Kaggle and contains images categorized by types of natural disaster. However, the dataset has been filtered and curated to include only 4 relevant categories, as I have said before. They are earthquake, urban fire, landslide, and water disaster. Only a small portion of the original dataset is used to keep the number of images across classes balanced and to ensure a clarity of classification. These following images below show an example of the dataset after the filtering process. As you can already see, each row represents one category and the dataset is visually balanced, which helps reduce model bias towards any specific class. So we have earthquake, urban fire, landslide, as well as water disaster. Thank you.
Hello, my name is Lauren, with the name of 260-210-8426. And now I will continue explaining about our methodology on our AOL deep learning report. So, first of all, I will tell you about our model building and training. So we use two different models that we developed and implemented to compare their performances and determine which approaches produce more accurate and reliable results. So the first one, we use CNN from scratch. It is a custom CNN that was built using Keras sequential API. This architecture includes two convolutional layers with ReLU and max pooling. Also, we do dropout layers to prevent overfitting and flatten dense layer for classification. Here's the screenshot from our code. And from this, we can know that the total parameters in the model amount to about 7.39 million with no untrainable layers. Maybe you can see it clearly through the code that will my friend explain at the end of the video. And the second one, we use transfer learning with EfficientNet B0. It's a pre-trained model known for its optimized performance and smaller size. This used TensorFlow. This model includes multiple convolutional blocks, activation functions, batch normalizations, and dense layer adapted for these four class problems. So here's the screenshot also from the code. Now you can know that the model parameters is about 4.21 million, in which about 4.04 million are untrainable, indicating its dependency on the features learned from ImageNet. Next up, I will tell you about the results and the analysis from our code. So to evaluate the performance of both models, custom CNN and efficient net B0 or the transfer learning, we observe their accuracy and loss over training epochs. So maybe from the report, we will show you in separate ways, but if you want to see it in the full one, you can see it in the code right here. Okay, so first one for the custom CNN model, here's the chart that you can see. We can know that the training accuracy gradually improve and period around 65%. It also shows us that the validation accuracy peak slightly higher, reaching up to 72%, suggesting the generalizing well model. Both training loss and validation loss decrease steadily, settling at around 0.8, indicating a consistent learning process with minimal overfitting. So from the CNN model itself, there are some strengths which there are slightly better validation accuracy compared to training, a good indicator for generalization. Also, the strength is relatively small and interpretable model with all training parameters. But there are also limitations for the CNN custom model. There are slight fluctuations in validation accuracy, suggesting some sensitivity to input variation, possibly due to limited data size. And now for the transfer learning. Here we can see that the training and validation accuracy played around 53.2% with little improvement throughout 50 epochs. It's so different from the CNN one, which starts on 50% until and reach up until 70 something percent, and here's only from 51% until 53%. So we also can see that the loss reduces gradually but remain higher than the custom CNN model. The majority of the transfer learning parameters are untrainable, which is up to 4.04 million, meaning limited fine-tuning happens. But from the transfer learning itself, there are some strengths, which are fast convergence with early stabilization and also low risk of overfitting due to frozen layers and smaller trainable parameter set. And the limitations for the transfer learning is underperformed, likely due to insufficient adaptation to the specific dataset. So for the summary and the conclusion, my friend Aidan will explain. Thank you.
Okay, so continuing with the explanation, I'd like to give a rundown on the code we put together to develop the models. So here is the code. We first began by mounting the dataset from Kaggle, where we downloaded the images from Kaggle to a directory in Collab session, and then we targeted the classes as instructed, them being earthquake, urban fire, landslide, and water disaster. And to ease the analysis process, really, we copied these images into a freshly created dataset a freshly created directory named the disaster dataset. And as we can see, there is a significance a significant class imbalance between the classes, with the water disaster having more images than the rest. This might influence the model's accuracy later on. Now we proceed by showing samples from each disaster class. We chose on 5. And as you can see, they are AI-generated disaster images, but it's irrelevant to the model development process. Just want to point that out. So first off, we prepared the data set. We declared the image size and the batch size. We also did augmenting and scaling for the image. And we also split the dataset naturally into training and validation with an 80/20 ratio. So we begin the model development. For the first model, which is the custom CNN from scratch, we define the following. These are the parameters. We decided on 32 to 60, increase to 64 filters, a 3x3 kernel size, and the activation function of ReLU. This is to prevent vanishing gradient, and the input shape as follows. The max pooling 2D is to downsample the features to reduce computational load, and we implemented the dropout to reduce overfitting. We then flattened the 2D features into one-dimensional 1D before feeding it into the dense layers of 128. And here we implemented regularization again as to combat overfitting, a dropout, and for the output layers, since we have 4 classes, so we decided on 4, and an activation function of softmax, which is relevant to usually image classification cases. And so then we compile the model. This is to configure how the model learns, trains. The optimizer is Adam, categorical cross entropy as its loss function, and we observe the accuracy metrics. There's follow. Also, we implemented an early stopping callback where we monitored the validation loss and a generous patience value of 5. This is done to automatically stop the training process if the model's performance doesn't improve significantly after several iterations, and it prevents overfitting, and also it reduces the computation load. And see, we just trained the model. We fit it into the model, and we decided on 50 epochs. And training result shows that it stopped on the 17. The result I will discuss later. And for the second model is the transfer learning using EfficientNet BO, a pre-trained model with less than 10 million parameters. So we first loaded the base model, and then we freeze the layers of the base model. Why is this done? Because we don't want to lose the knowledges the pre-trained model has acquired in its respective training process. And so we'd like to translate its expertise, the pre-trained model's expertise, into when classifying our dataset. And so then we add a custom head. Why is this done? So the pre-trained model can identify our classes. We also did an L2 regularization to prevent overfitting. We implemented dropout. And for the output, again, it's 4 classes. And so continuing, it's pretty much the same process where we compiled the model, and then an early stopping callback is implemented, with the difference being the patience of 7. Since we're dealing with a pre-trained model, I'd like to be more generous with the patience of this callback function. So we then just train it with, again, 50 epochs. And this model took a while to train, mind you. It used up all 50 epochs. And once we're done, we compare the training and validation accuracy and loss, which is how we acquired the chart provided in the report. I believe my friend has explained enough about the results, but I like to add a little. So for the custom CNN, when it comes to accuracy, they both show rapid initial increase in training and validation, with the validation accuracy slightly trailing. What I'd like to highlight here is the validation accuracy improved but fluctuated more. This might indicate the occurrence of an overfitting. And for the loss, training loss significant decrease in the initial 10 epochs, yeah. Subsequently, training loss continued to gradually decline while validation loss again became more volatile. This divergence being brought up again indicates an overfitting. Meanwhile, how does it compare to the efficient net BO, the pre-trained one? Well, it shows a very rapid convergence in accuracy during the initial 0 to 5 epochs. Well, both training and validation quickly stabilize at the low value of around 53% while remaining largely stagnant. So what's to note here is that the fact that the validation almost perfectly mirrors the training accuracy. This indicates no overfitting. However, the persistent low accuracy suggests an underfitting or difficulty at learning meaningful features. And the last, also both experience the training and validation experience a very sharp decrease in very first epochs. And following this, both losses quickly plateaued. So similar to accuracy, the loss, they remain very close, confirming the absence of overfitting. However, the high stable loss value reinforces conclusion of underfitting. So how do they compare? The custom CNN, it appears to suffer from overfitting. Meanwhile, the pre-trained model suffers from underfitting. And so for the learning capacity, custom CNN seems to have a higher learning capacity with peak validation accuracy of around 71. Meanwhile, EfficientNet is 53%. So funnily enough, despite the simplicity, the custom architecture might be better suited for classifying or dataset. And the convergence speed both relatively quickly in their initial learning phases. However, EfficientNet reaches its stable performance much faster than the custom one. And also, I'd like to highlight that maybe the poor performance of EfficientNet BO, the pre-trained one, is due to the impact of pre-trained weights which the factors cover dataset mismatch, insufficient fine-tuning, data characteristics, and lack of unfreezing or rare retraining. So I'd like to return to our report. Well, we would like to conclude that in this classification task, clearly the custom CNN model outperformed the pre-trained one. And while transfer learning is usually beneficial, it may not provide the optimal results without proper refinement, especially considering the data set we analyze is small. So this observation is in line with the findings of past researches, such as that in research by Chapman showed that in data stressed environments, enhancing pre-trained models can be beneficial, but the degree of enhancement, how much should be tweaked, is highly dependent on the size of target dataset and the similarity between the source and target domains. Also, a study by Zheng showed the relationship between numbers of trainable layers in pre-trained model and the size of the initial dataset. The study shows that freezing too many layers in a scenario with limited data, like in our case, we have a small data set to begin with, can lead to overfitting, which results in the poor performance. And so these insights strengthen the idea that while transfer learning offers a robust tool, its effectiveness relies on careful adaptation to the specific characteristics of the target data set. So despite the CNN at the end of the day performing better, we might see with tweaks in a future project, we might see the pre-trained one overperforming the custom one, but we've yet to find out due to the lack of opportunity to do so. And that sums up our presentation. Thank you for listening, and till next time.